Now recall that our function was f of xy equal x squared plus y cubed. We can write this out directly in terms of t. X is a cosine of omega t, so we have cosine squared of omega t. Y is 2 sine of omega t, so y cubed is 8 sine cubed of omega t. And we can then directly take the derivative of this expression with respect to t without running through the chain rule the way we did before. That has a couple of advantages. One, it illustrates the validity of the chain rule, at least makes it plausible. And we can also use it to check and see if we get this same obnoxious term here that gives me something I can't visualize. So our derivative is very straightforward. The derivative of the cosine squared of omega t, well, that's the square of a cosine of omega t. The derivative is going to be the derivative of cosine omega t, which is this, times 2 cosine omega t, the composite of the squaring function, the cosine function, and the omega t function. That's something you should be able to see, but if you can't, you should write it out. You need to practice. Okay. And then the derivative of 8 sine cubed of omega t, well, we have the 8 out in front. I was going to put the 8 in a little later, and then I decided to put it in front here because I didn't really have a good place. So that 8 looks kind of bad, but I think it can be read. I think it can be read, right? I think it can be read. Okay. Now, so we have the factor of 8. The sine cubed, that's a cubing function. The derivative of the cubing function is 3 times the squaring function. So we're going to have a 3 sine squared of omega t. The inner function of the cube is the sine of omega t, whose derivative is omega cosine of omega t. And now the simplification becomes very straightforward. We're going to have a negative 2 omega, a sine and a cosine of omega t. And we're going to have an 8 cosine times the sine squared of omega t and times the 3 omega. That's going to give us a 24 omega times the sine squared cosine. We factor out the 2 omega sine cosine, and by darn, we still get a negative 1 plus 12 sine of omega t. Same result. We conclude, I think, and we'll look at it a little more closely in a minute, but that curve does stop rising for an instant. Okay, somewhere around here, that thing somehow manages to level off, and I'm still not sure how that's happening. When I look at the functions, I don't see it. But that should happen when the sine of omega t is 1/12. This is going to give us 0, which means our derivative of f with respect to t is going to be 0, so that f is going to, for an instant, stop increasing, meaning that our curve is going to stop rising. That occurs when sine of omega t is 1/12, and that's easily solved. T is, we take the inverse sine of both sides and then divide by omega, and we get t equals 1 over omega times the inverse sine of 1/12.